Lesson 10.6 is all about exponential growth and exponential decay. We talked earlier about looking at a graph and determining whether it's exponential growth or decay based on whether it's going up or going down, or looking at a function and saying whether or not it's exponential growth or decay. Looking at that b value and saying, is it in between 0 and 1, or is it 1 or greater, that b value? So, in general, in a real-life situation, we would say that certain assets like homes, so your home, would appreciate in value. And what that means by appreciate means its value increases over time. Your home is worth more today than it was 10 years ago, in general. Other things like cars depreciate in value. So that's exponential decay, which means over time, cars will decrease in value. If you've got a car that's 5 years old, it's worth less now than it was 5 years ago. New cars are worth more than used cars. That's not anything new. We should all already get that. So, how that looks though, an exponential decay function should be modeled like this. Y equals a times 1 minus r to the power of t. Exponential growth should look like this. Y equals a times the power of 1 plus r to the t. The big difference here is this is a plus r, this is a minus r. If it's 1 minus r, and that r is a decimal value, that means that we're going to have a value in there that's in between 0 and 1. That's why it's decay. And if it's plus r, it'll be greater than 1. That's why it's growth. So, in all of these cases, though, r is the percentage of increase or decrease. So if it grows by 10% or if it decreases by 30%, it would be that percentage of increase or decrease that is expressed in a decimal value. So if it was 30%, you would use 0.3. If it was 5%, you would use 0.05. Now, those are how you look at things if they're growing and you're checking them every so often. But if they are being checked kind of continuously, or if they're continuously growing, kind of the natural way of things, like a cell is naturally growing. It doesn't just one day say, oh, I'm instantly going to grow another cell. It's continuously happening over time. So we would say then that we use that continuous growth, or the e value, and if it's exponentially decaying, we have to have e to a negative value, e to the negative k times t, times a equals our y, or if it's growing, it would be a positive k, so y equals a times e to the positive k times t. In all of these cases, a is the initial amount, so it's what you started with. T is your time in years. Now it's not always in years. Depending on the problem, it'll tell you what t is in, but usually it'll be in years. And a special note here is that our k value is 0.00012 if we're working with carbon-14. Carbon-14 is a special isotope of carbon that depreciates over time, exponential decay, so it kind of runs out of itself over time, so you can use that to find out how old something is. It's called carbon dating. So let's see exactly how some of these things work. A cup of coffee contains 130 milligrams of caffeine. Don't tell Mrs. Green, though. If the caffeine is eliminated from the body at a rate of 11% per hour, how long will it take for 90% of this caffeine to be eliminated from a person's body? So if we're talking about elimination, we're talking about exponential decay. So we want to use the formula y equals a times 1 minus r t, exponential decay. And what kinds of things do we know? We know our initial value is 130 milligrams. A equals 130. We know that the rate of it disappearing is 11% per hour. R equals 0.11. Remember, we always express our percents in that decimal, 0.11. And if we want 90% of it to be eliminated, that's the same as saying 10% is left, and 10% is 0.10 or 0.1, and we do 0.10 of our initial amount, which was 130 milligrams, remember, means that we have 13 milligrams left. So our y value of how much is left is 13. What we're looking for in this case is t, because we want to know how long it takes for it all to be gone from the body. So we'll just plug in what we know back into that formula. And we would say then that 13, our y, what we're left with, equals what we started with, 130, times the value 1 minus r is our 0.11, that's our rate, how much it's going away, times our time t, which we don't know what that is yet. So we'll just do some simple algebra to get rid of some of these numbers. We'll divide both sides by 130. 13 over 130 is 1/10. 130 over 130 would just be 1. So we're just essentially getting rid of it from this side. In here, we have 1 minus 0.11, which comes out to 0.89 to the power of t. So this is our simplified version. Now here is where our properties of logarithms come into play. We can either use log or we can use natural log to solve this. I'm going to use natural log because I usually think of natural log as more of our growth and decay function, so we'll use that one. So we'll take the natural log of both sides. Natural log of 1/10, or 0.1 is 1/10, equals the natural log of 0.89 to the power of t. Again, going back to using our properties, we would say the natural log of 0.1 equals t times natural log of 0.89. Because we had t out here, we can move it out front. Now we'll divide both sides by natural log of, I don't need the point, natural log of 0.89, which leaves us with natural log 0.1 over natural log 0.89 equals t, which then in the end means if we plug that into our calculator, t would come out to 19.75 hours. So it takes almost 20 hours for 90% of that caffeine to get out of your system. Some strong coffee. Let's look at this situation. The half-life of sodium-22 is 2.6 years. What is the value of K for sodium-22? Again, sodium-22 is another isotope. It's a certain kind of sodium that takes 2.6 years for half of it to be left. So that's an exponential decay function again, and it's happening continuously. So we would use y equals a times e to the negative kt. Now, we don't know exactly how much we have, but we know that there's only half left in the end. So half of a equals a, how much we started with, times e to the, we don't know our k value, so negative k, but we know that it takes 2.6 years for it to come down to half. Other things we know, we can take out a right away, divide both sides by a. So we're left with 0.5 equals e to the negative k times 2.6. So again, use our property of logarithms and we'll take the natural log of both sides. ln 0.5 equals ln e to the negative k times 2.6. Well, anytime that we have ln of e, we can get rid of it. So we just have ln 0.5 equals negative k times 2.6. So all we have to do is divide both sides by negative 2.6. So we get ln 0.5 over negative 2.6 equals that k value. And again, plugging that into our calculator means that k equals 0.2666. So that is our k value, what it is appreciating or depreciating over time. And we'll get to this next one in our next video.